So, okay, good. We're recording. Let me delete this. So hopefully today we have slides. Let me see if that works. And we didn't finish. So last time we didn't finish the evolution part. So we didn't talk about evolution, which should be talking today. And also, I remember quite a few people said they do have experience in machine learning, and there were some people who had no experience in machine learning, right? And there were some people who were just like, well, I have no idea. Which is good. So we're gonna tackle this today. So machine learning basics. For those people who are experts in machine learning, maybe it's a nice kind of a refresher, hopefully not boring. So maybe you will learn something new as well. But I think it's important to talk about these things because they kind of underlie, everything we're doing in natural language processing these days. So we're gonna be talking about basically supervised machine learning, which is like 99%, well, not 99%, but the majority of machine learning is about supervised machine learning. And we will be talking about evaluation and some technical stuff such as loss functions. And the goal is to understand really the foundations of what machine learning or supervised machine learning should be about. So then later, when we talk about deep learning and natural language processing, we know kind of, oh wait, this might be understood as an like sub area of machine learning or there's some intersection between those two. So we'll start with a little bit with notation. I mean, I'm sorry. Okay, who who hates mathematics? Raise your hand. I mean, it's fine. I'm just curious. Like, okay, yeah, good. So that's great. So we love mathematics. That's awesome because we're going to be using mathematical symbols. And if you might have seen, I'm using LaTeX for typesetting these slides because math is beautiful in LaTeX. So if I were doing this in PowerPoint, we would have like lots of pictures of cats because it's easy to put pictures of cats in PowerPoint, but it's hard to typeset. Well, it's impossible to typeset beautiful mathematics in PowerPoint. So that's not the case. Okay, as long as we don't have popcorns here, I'm fine with that. Okay, but I don't keep going. So, a little bit of notation. So we have things called vectors. I mean, everybody had like linear algebra. Everybody had calculus. Good. So this is not surprising, but just what we were talking about. So we have vectors. I think actually vectors in physics or mathematics are just are these column vectors, right? I mean, typically you have like column vectors, and then if you wanna treat them as a row vector, you write like these ugly things like x transposed, right? I think folks in NLP are actually using or deep learning. It depends. So we never know what the vectors are, whether they are column vectors or row vectors. Mostly in this lecture, we'll be using row vectors. So keep that in mind. If you're in doubt, just ask. But we'll be using like row vectors, and this is just a arbitrary decision, so to say. So it's by convention, people are using different notations, and as you will see, like mathematics is super ambiguous, in many ways. So sometimes list of number is a vector. So remember our exercise last week, we were talking about shapes and different dimensions and multidimensional arrays. And we have now vectors, which could be column vectors or row vectors. So you understand, why it's kind of messy. I mean, its underlying mechanisms are simple, but the ambiguity of that is kind of makes it sometimes maybe hard to understand. Okay, any questions to vectors? Good. A list of bunch of numbers. List of numbers. Then we have matrices. No surprise here. So we are saying a matrix here. So we're using uppercase, capital, bold symbols. And what is this? What is this beautiful R? Yeah. This is a set of all real numbers. And we're saying, and what does it mean? Like R, which looks like to the power 2 times 3. It's the dimensionality of this. So it's basically saying we have 2 times 3 matrix of real numbers. Okay, everybody's fine with that? Okay, shouldn't be surprising. So this is an example. And we're using the standard indexing from 1. So, and here's again the discrepancy between the mathematics, which kind of indexing things from 1 to n, and computer science, where we tend to index things from 0 to n-1. Okay, so keep that in mind. If you implement something just blindly following the instructions, might be tricky. And then we have scalars, which are just lowercase numbers. Okay, so shouldn't be any surprises here. Ambiguity. Okay, so we have dot, which is some sort of multiplication, and it also, I mean, it really depends on the context. So multiplying scalars, multiplying two vectors, what does it mean? Well, it could be a dot product. So everybody knows dot product, multiplying each element with each element from those two. We'll come to dot product actually in a couple of next lectures about the actual, so the meaning of dot product in, well, or interpretation of the product. Anyway, then we multiply matrices and vectors. So this is vector times my matrix and two matrices, and you should know the rules. Like if there is something you should refresh from a linear algebra is how to multiply a vector and a matrix or two matrices together. Okay, that would be great. So there's simple rules and just would be great to refresh them. So you should be able to multiply matrices. Okay. That's it for today with notation. I mean, there's nothing surprising in there. But let's talk about supervised machine learning. So what is our problem? So we're trying to learn something from data. So what is the data? We collect some. We are talking about data last time, basically. We have this corpora, like IMDb sentiment reviews. We have natural language inference, so a couple of sentences. We have many other things, so data sets. And we're trying to build machines which kind of predicts the label of the data, right? I mean, the sentiment analysis task was, for example, given a new review, I want to predict whether it's positive or negative, or what's the sentiment of the review, for example. Or having it a text and hypothesis, two sentences, does it entail or does it contradict or is it neutral? So this is the labeling task, and we want to automate it, obviously. So how we set up this problem is that we have some label data points. So now we know what labeling is, which means like we know what the actual label is. Was it negative? Somebody labeled it manually, or we just found it on the internet. Somebody did it in the first place. So we have these label data points. We call them samples or examples or points. So I'll be using samples and examples kind of interchangeably. So there's many ways to call them. So examples. So one single example, and it consists of a vector and a label. Typically, there's there could be more things, but typically we have the x is a vector of which we call features. Is there here somewhere features? No. So in standard machine learning, we call them features, the input basically. And then we have the y's, which is the label. So for example, here, y is something like a real number, I guess, but it could be also a vector. So where we say like, oh, it's a vector of these different categories, and basically one of these categories will be 1 and the others will be 0. Okay. I think we'll get to that, how to represent that. So we have these pairs of input and output, right? Does it make sense? Any questions or unclarity? We have those. So it's for example, X would be text and Y would be positive or 1, or if it's like a binary task, positive or negative. So we would say 1 or 0. And then we have another review and again, 0 or 1 as a label. So this is the data set. Then we have a model, which is sort of it's basically some function. So it's a function which has some parameters. What is this very ugly symbol? Say again? Theta. Theta. Okay, good. Theta. Because why not? So it's theta. Typically, we use theta for some parameters. So if you see theta, it's kind of like maybe it's some parameters of some model, but it could be anything. Like the choice of numbers and letters is really arbitrary. So somebody just said like, let's call it theta. I guess maybe there's reasons. So there's different kind of cultures also, like how to notate things. But theta are typically parameters, and x is input and y is output, right? Because then we have a function that the output is some function of the input. Okay, well, yeah, sure, there's a function. So we plug something into the function, and the function outputs the label. Okay, so far so good, I guess. So model takes input and produces the output. So we are using this y hat here. So this is y hat, which is somehow should be almost the same as the true label, but who knows? So maybe the function is not perfect. So the function is outputting something which we want to be perfect, but who knows? Maybe it's not perfect. It doesn't have like perfect performance, so to say. And then we specify some sort of loss function. Okay, so this looks very ugly, but let's look into that. So let's start here. So what is this thing again? So this is taking some input y. So we're iterating over all inputs. Okay, so we're iterating over all the data set because we have endpoints in the data set. Cool. So it's taking the input and pushes it through the function. So this is basically the y hat, right? This is what we have here. So this is the y hat, which is what the function is predicting, and this y is the true gold label, right? This is what we know. This is the true label, and this is what the function predicts. Everybody's with me? Good. And since these are two numbers, we can just make a difference. And of course, the difference could be negative or positive, so we're just gonna square the difference. So this will be always positive. Okay, so what does it mean? So for example, if the gold label if this were 1, for example, it's a positive review. Okay, so if we have binary task, we typically say it's 0 and 1. Sometimes it's -1 and +1, but typically 0 and 1. And like if this is binary task of sentiment, we would say if it's a positive review, it's 1, and if it's negative, it's 0. So this would be, for example, 1, and the function predicts something which is wrong. So the function says, oh, by the way, this review, I mean this text, is it's 0. So if this comes out 0, then we make a difference and square it, which is some sort of like how wrong are we on this example, right? This is like the difference between the prediction and the difference between the true label as we have. So, and what is this doing? What are we doing with this? Because this was for one single example. What we're doing with the sum and the division here, the fraction. We are averaging over what? Yeah, so we're averaging over, we're iterating over the whole data set, right? And for each example, we're taking the squared loss and we're just taking the average. So basically our loss of our function of our model is average over the entire training data set. Okay, so in some cases this will be maybe perfect, in some cases this will be not perfect, and overall we just take the average and tells us like, oh, how good I train on the training data, so to say. Okay, any questions? Good. Why? Okay, I have a question. Why this? So we want this to be positive number. Okay, good. What if I say, okay, I don't want to square it. Let's take absolute value. Would it work? So who thinks that absolute value is a good idea? Who thinks it's a bad idea? Or any other opinion? Yes, in the back.
Well, the thing is, if the absolute value is taken, the quantity that comes out will just be the difference between the two values. There'll be just a scalar difference between the two values, not the degree in which the prediction is wrong.
Well, it gives you the difference between the wrong prediction and the good and the true label. So it's just a different scale. It's not a squared function, it's just a linear function. But it tells you it's a positive number and it tells you, you know. So I would say absolute value would work as well as a loss function. Why not? It tells you the difference between the wrong prediction and the good prediction in a different way. And maybe there are some advantages of having it squared, because maybe some derivatives and blah, blah, blah. But overall, the loss could be anything, which is, we'll come to the loss in detail later, but it could be also absolute value, but you know, this is called squared loss. Squared loss function, and it's just convenient for some reasons in some setup. Okay, but this is just one example of a loss. So the problem is clear. We have data points which have labels represented as a vector of features and the actual label. Then we have a model, which is a function, is basically a function, input, output. And then we say how well the model predicts or the function predicts on the training data is the loss function. So this is our setup. And now we can work with that somehow. We formalize the problem of, oh, I want to predict, you know, train a model for predicting reviews. Any questions? Good. So the learning, our goal is to find these parameters. What is that thing again? What was it again? This thing? What was it? What is this? Theta. Okay, cool. Just checking if you're not sleeping. So which is fine. I mean, it's very early. So to be honest, yeah. I drink a lot of coffee in the morning to survive. So our goal is to find such parameters theta that actually minimize the loss, which makes sense because now we know the loss is over the entire data set and it's different between the good one and wrong one. So we want to make it as small as possible. So we want basically be a good predictor in a way. So our model fits the training data better. Oh, okay. Now we understand, if you're talking about fitting a function, then what it actually means. We can fitting the data. We can also overfit if our model is, okay, this is interesting. So overfitting, what does it mean? So maybe the parameters, we have so many parameters. So the model is huge that actually the model can remember everything from the training data. And then we have like a zero loss. Is it possible? Well, why not? I mean, if you look here, then basically what it's after training, we would say for every training data example, the difference would be zero. Then we have zero loss, which means the model can correctly predict each training example, right? Is it a good thing? Why not? Why not?
Because due to trying to fit different parameters, it might overshoot on the, for instance, like the dimensionality of the original function.
Overshoot. I think you're on good spot. So let's try some other explanations. Yes, in the back.
If it's correctly predicts every training data, it means that it doesn't generalize well.
Oh, generalization. Okay, generalize well. What does it mean, generalize?
Predict somehow correctly on out of training data, so test data.
Oh, test data. Okay, cool. Yeah, exactly. Because if we train the model on the training data and remembers the training data, is the model of any use for something which we haven't seen before on a new fresh data coming in? And we don't know. So maybe not. And the overfitting typically means that you can remember all the training data and then it won't generalize on new test data, something which is coming. So for example, you train a system, you put it in production and you had like 100% or zero loss on your training data and you put it in production and it's just a disaster because, well, it doesn't generalize to new things coming in. Yeah, so it could be due to overfitting. On the other hand, like modern transformers actually are super huge models. I mean, as we saw last time, like some 70 billion parameters, it's huge. So it can absolutely remember a lot of things, and it does generalize. And people are saying, why? And nobody knows. So if you want to do PhD, then pick this topic. Why deep learning models, transformers, which are huge, why don't they overparameterize? Why don't they overfit? Because they do remember training data, but they do also generalize well. What's the theory behind? Who knows? I mean, there's theories, but we don't really know exactly. So that was the overfitting here, okay? Any questions to overfitting? Does it kind of make sense now to what you were thinking about? Okay, cool. Because you're using different vocabulary. So it's also, interesting, like people are coming from different communities and so like overshooting or
Yeah, I was thinking of like because overfitting usually entails that you are trying to fit a higher order polynomial to a lower order.
Because you come from machine learning background, right?
Yes.
You're fitting polynomials and you say the more degree of polynomial I'll have, the more I'm fitting the curve. Yeah, that's right. But
it comes up to the same thing that the high polynomial doesn't generalize well to the lower order.
That's correct. Yeah, that's correct. So, bias, what is this? Variance bias trade-off. Yeah. Okay, you can ignore this. That's fine. That's not important because, I mean, transformers are just generalized and they're overfitted. So what's going on? Okay, generalization. I think we actually covered that. The actual goal of machine learning is to generalize well of previously unseen data. So how do we know it actually generalized on some new data? We're gonna split a data set into training and test set. And models must perform well on test data, which are hidden during learning. So we use here our data set, we just split it somewhere. And we say this is training and this is for testing. And we are doing this kind of parameter optimization on the training data. And then we say, okay, we're ready. let's try on test data. And if it works, then you can, I don't know, you can sell it and get rich or not. So generalization. Okay, we covered that. So the machine, as we now understand, the basics of machine learning are three components, which is data, models, and the actual learning. So we'll cover the data and models, and the actual learning will be part of maybe next lecture, like in detail, one of the algorithms. So what is the data? Again, this is the data set. Excuse me, this is a set of these tuples, input, output, and why I'm repeating this. Sorry, it's a glitch in the slide. So this is basically what we covered already. So I can skip this slide. This is just the same thing as we told before. So this is the data set. One assumption about the data set we're usually doing, and this is very strong assumption, which is in reality it's mostly violated, or who knows, it's hard to prove. We are saying that the data set is independent and identically distributed, IID. So what does it mean? Dot is missing. Independent. So it means that any two data points, xy and xj, do not statistically depend on each other. So they are kind of, if there were a random process from which you were kind of drawing your data, then these draws are independent from each other, so to say. So some formalism of machine learning theory is saying, oh, there is an underlying probability distribution, and from this probability distribution, we are drawing these examples. So we're sampling from some random process, and these draws are independent. I don't actually have a good example of like how that would be in text, because if we have a data set, for example, okay, this is interesting. So we have a data set of these movie reviews, for example. So we have review 1 and review 2. So are these of the same movie, for example, are these IID? Like, but who knows? So if we're saying they are drawn from some underlying, let's say, probability of language, then we might say, okay, these are kind of independent because these are two realizations of language. But who knows? I don't know. I don't really have an answer, actually, to be honest, right now. Are these examples IID? Well, so what we're doing, we just close our eyes and pretend they are. Okay, so this is the assumption. These samples are IID, and we just, then just forget about the problem and run the machine learning on top of that. And that's fine. Sometimes it doesn't matter. But just be clear about, there are some assumptions of the data sets which we actually violate, and it's fine. Like the overfitting thing, yeah, well, maybe that doesn't matter. IID, is it really important? Maybe it doesn't matter. So for some example, for some applications or some machine learning theory, it's really important to have IID samples. For some, maybe it doesn't matter. So we're doing the business as usual. I just don't care about this problem, okay? But that you've heard about it. So IID is like, independent, identically distributed data. Any questions? Okay, then we come to the model. So we call the model also a predictor. Do we? No, I don't think so. Actually, so this theory comes from a book called Mathematics for Machine Learning, which is freely available at GitHub. It's published by MIT Press, but you can get a PDF. It's kind of nice introduction. So if you're interested in more theory or mathematics, like underlying of machine learning, then it's actually a great book. So they call it predictor there. Why not? I mean, predictor is a function from features to output. Okay, right. We take our text, then maybe extract the features, make it a vector, and then try to predict the label. No surprise. If we are classifying things, we typically predict a probability distribution over categories. Okay, so then the output is also vector. And here the vector is of a size of number of classes. So for example, if you're classifying our documents into 3 classes, for example, here by topic, so is the document sport? Is it about politics? Is it about business? So we can map these to positions in a vector, and then we would say basically if a document is so we have a document which is about politics, we would then represent the y vector as follows. So it's called one-hot encoding. And why is it one-hot? So it's basically saying the only position which is actually correct. So politics equals to the first position, right? Is set to 1 and the others are set to 0, right? So how would the vector of, for example, of a label of business would look like? Business vector. Say again?
0, 0, 1.
It would be 0, 0, 1. Yeah, because the last position of business is the correct label and the others are 0. Okay, so this is what we're doing. Any questions? One-hot encoding. Cool. And as we are trying to predict basic, so this is the gold standard label, and we are trying to predict this exact vector, and what we are end up with is maybe predicting almost the vector. So if X were something about politics, maybe then we would get a vector of 3 numbers, which is some sort of histogram, right? I mean, 0, 0, 1. So if you have position 1, 0, 1, and 2, so we have something small, then we have something very huge number, and then we have something small. So right, it's a histogram of over these categories. So 0, 0, 1, 0, 82, 0, 17, something like that. And this is also a probability distribution, right? Why? Well, I mean, it's not by chance, by design, basically, because they sum up to 1. So we're trying to predict the probability of the output. So for example, this will tell me that the output is with probability 0. The probability of being this politics is 0.82. The probability of being sport is 0.01, and the probability of being business is 0.17. So this is what the function is predicting. It's trying to predict the correct label, right? It's trying to predict this. But sometimes maybe the algorithm is not sure and just predicts something like this, a probability distribution of the classes. Any questions? Doesn't make sense? Okay. All good. So, and we try to predict the best parameters, the theta, and of course the generalization. So the resulting predictor should perform well on unseen data. So this is what we want. So we have 3 distinct phases with working with models in learning. And this is, well, once you train the model, you do a thing called inference, so a prediction. So what does it mean? You have something, just the features are coming in, so the vector of features, or maybe the text, which you have no idea what it's about. And your model will do the classification or anything else, typically classification. So the model is already trained. The model has the best parameters on some training data, and then you use it in production. So basically, I don't know, anything which you're just using on a daily basis, every machine learning system which is out there and you're using is doing inference. You're not training the system, you're just using it. So it's predicting the new input. I mean, give me an example of a text which is actually on the day, what you're using on a daily basis. Let me see. Oh yeah, for example, okay, typing. So if whatever you type on your phone, it's doing, what is it doing when you type? How you type on the phone?
Predicting the next word.
Oh yeah, okay, it's predicting the next word. So it's like, oops, predicting the next word, making your life faster and easier and whatever. So it's a classification. It's basically inference because underneath there's a language model running and it's doing inference. So it's like whatever you type in is the input and the output is the next probable word, and it's giving you the choices and you just pick up from the top 3. It's inference of a machine learning model. Okay, so then in order to get there, we need to train the model or estimate the parameters also. And also there are some, it's not only about finding the best parameters, but something called hyperparameters, which means, for example, you can make choices about your model. So you can choose maybe how big the model will be. Are you going to train a 70 billion transformer or just something small with 20 parameters? So who knows what works better? Well, I would say like the bigger works better mostly, but maybe there's some design choices. So which are called hyperparameters. So you wanna make sure that you also find the best hyperparameters on some training data. So there's basically these three steps. Any questions or any surprises here? Does it make sense for those who have never heard of machine learning? That's the most important question. Does it make any sense? Okay, that's great. If you have any questions, just ask. That's great. So I mean, we need to find a common ground. That's the whole idea. Okay. What? Yeah, we talked about this already. Just we're finding the function. We have y hat, which is the prediction, and yeah. So we sorry. Okay, no. Okay, we did talk about most of that, but the good parameters theta. Why is it theta star? Yeah, because we don't know the true theta, so we estimating. So something which we estimating is typically written with theta with the star. So the best parameters could be multiple parameters. You know, who knows? If it's a vector of numbers, there could be multiple best solution for the model. So we trying to find something which works best if we can measure it with the loss. Okay. We are talking already about the loss function, so let's dig deeper. So loss function, we had the example of the square loss, right? I mean the true label minus Praetor's output squared. So there are multiple loss functions which we can use. So we are discussing the absolute value as well. In general, the loss function is something which takes the true label, takes the Praetor's output, and output something. What is R plus? Yeah, it's positive number. So it's something like, I would say 0, infinity. So positive numbers, something positive. Why? Because we wanna, I mean, there's a minimum, right? I mean, if we perfectly fit the training data, we have 0. So it can't be any less. And it could be as big as it can. So it's representing how big an error we made on this particle prediction. That's correct. And our goal for finding good parameter vector is actually to minimize the average loss. So this is the average loss we're talking about on the set of n training examples. All right, this is the trick. We have only limited training data, so this is all we have. So we want to find a function which kind of minimizes the loss on the training data automatically. And at the same time, we hope that it will kind of generalize well on the unseen data. This is the holy grail of machine learning, basically trying to learn from finite data, being able to do infinite computations. Is it hard, even with lots of data? Give me an example. Why is it super hard, even with lots of data? Do you have an example? Yes.
Put in a picture that there's move like a landscape of where you can end up on the block, and there's several local minima.
Okay, you're talking very technically. This is great. So there could be we're minimizing a thing on a loss function, and you're saying the loss has a landscape. Okay, that's great. And there could be multiple solutions, like which is local minima. In a way, yes, you're right. Maybe it matters, maybe it doesn't matter. Yeah.
Pictures of different types of doors.
Yeah. Yeah.
Or yeah, and the model would say it's a door, but suddenly we show it a picture of the doors.
Okay.
And it also has.
Yeah, right. Yeah, right. So okay, I see your point. I would say yes. Okay, so the model has never seen something like a horse in the training data, so it will keep thinking it's a dog because it saw only dogs. Is it realistic, really? I don't know. I mean, this example is kind of, I see the point, like as an example, but it's a good one. I'll give you another example, which is actually quite problematic these days. So ChatGPT or these language models, they were trained on the internet, right? I mean, you took basically the internet, all the training data, which you can basically crawl from the internet, and you train the model, and then you fine tune it and whatever. So you throw everything you know in it, and you hope it will generalize well. That's the assumption. It does. as long as you behave nicely. But you can, there's these attempts like, can I hijack the model? Can I jailbreak the model? Can I do it, make it doing nasty things? Yeah, because you're going out of distribution of training data, and the model doesn't generalize that well on these kind of, muddy waters. So it's in the domains which it has never seen before, and the model is saying like, well, the model is saying nothing. I mean, it's not a person, but if I were the model, I'm doing right now, I have no idea. So I'll just generate the answer. Even though like it has seen a lot of training data. So it's a big issue. Like generalization is a really big issue. Okay, good. So let's move on. Square loss, we talked about it. So this is one example of the loss. We just take a square and we learn the parameters such that this thing is as small as possible over the training data. So we talked about this before already. And the generalization we talked about as well. So we're not interested in how the predictor works on training data, but on the test set. And this is, if there's something which you have to remember forever, ever, right on spot. So now I'm saying this, you have to remember. Everything before is kind of optional. But now you have to remember. Never train on your test data. Never. Why? Why shouldn't you train on test data?
Because at the end of the day, it will just remember what you have learned from testing, and this only works on the test data.
Yeah, exactly. If I show the exam right now, and everybody will score like 0.1, I'm saying, awesome. You're an awesome class. Like just remember.
We had this debate with a colleague, and he trains and then evaluates and tests it. But he trains only on training set and then evaluates on test set. But afterwards, he takes a test set and trains further through epochs and says, now it remembers everything and I can deploy it.
That's okay. That's a different story. But that's so what you're referring to. So I think I have slides on evaluation later on the cross validation and stuff like that. But so can you remind me of that when we come there? So this makes sense, this strategy, but that's not for the evaluation of your training model, it's for deployment. But for evaluation, never train or test on your test set because it will leak. And you might be thinking, of course. Yeah, of course I won't do that. So you'd be surprised how many people actually, it's easy to screw up. If you're using third-party libraries that splits your data sets into train and test, and you don't understand what they're doing, you just easily screw up. So there's bugs in the code, and then you get like super high accuracy, and then somebody comes like, you were training our test data, right? No, okay. It happens. So be careful. But on the other, so there's one more thing on that, and this is even more kind of subtler and even more dangerous. I don't have the reference here to this, but the paper showed. I think it's from a group in Prague, Ondřej Bojar, if I'm not mistaken, EACL 2023 or 4 this year, maybe. They won the Best Paper Award, showing that ChatGPT, so if you're asking ChatGPT, you're running the inference, you're not training the model, right? You're running the inference, so you're asking, well, generate me the next words. So what happens with the data afterwards? After you finish your session in ChatGPT, what happens with the data? Will it be deleted or will it be used for something else? So who thinks it will be deleted? Glad. I'm glad to see we're not naive. So what's happening to the data then?
Maybe used for other training sessions, but not ChatGPT, maybe other models.
So why not for training to GPT?
Data.
No, it didn't see the data. It saw it for inference. It doesn't remember anything from inference. So what will happen with the data? What happens with your data you type into ChatGPT? Sorry, say again? Salt? In a way, yes, salt for market, maybe for marketing. Yeah, maybe.
And it is mostly used to feedback to the model.
I might be used for feedback for the model in some way, but you need like human feedback. What's the easiest thing to do with the data? It's used for training. Like the next iteration of ChatGPT will just take all the internet plus all your data and just train the model again and again. So everything, right? Makes sense? It's trained on the internet. So, and the more data, the better. So you just take everything you have, and people are typing a lot of things into ChatGPT. So most likely what happens, and this is what the paper showed, most likely everything which you put into ChatGPT as inference will be used later on for training. Now, what happens if you have a problem like I don't know, like there's a IMDb data set which is old, and somebody says like, oh, I'm gonna try how ChatGPT works on that. So he types it, basically runs the prediction using ChatGPT on this data set and gets results like 85, 95%. And a half a year later, somebody comes and does the same thing. Where's the problem? Where's the problem? So again, you have a test data of the IMDb and you say like, I'll let ChatGPT to solve it. And you just type it in or copy paste and it solves the problem. You get results and you're happy to write a paper. Half a year later, somebody comes in and says like, oh, I'm gonna reproduce these results. What will happen?
I think that you get 100% accuracy.
Maybe you want to get like 100% accuracy, but the accuracy will be higher. Why? Because in the meantime, the model was trained on test data. Because it was saved by OpenAI, and then the next generation of ChatGPT was trained with your test data. So the test data is now part of the pre-training data of the next generation ChatGPT. So whatever you're trying to test, if it has been seen before, then you broke this assumption. You leaked test data, and you have no control whatsoever. So if you do anything in research and want to be reproducible, don't use ChatGPT, because you have no idea what's in the training data. Nobody knows. There are open source models where you know exactly what's in the pre-training data of the model, so then you can make claims. But you cannot make any claims about the training data of ChatGPT. So that's problematic, and it's like kind of subtle leakage of training data. But this paper showed kind of the tendency of the public, data sets which are used for benchmarking, that actually over time they're getting better. Why is it possible? Of course, somebody just typed them in, and then they'll be stored forever, and maybe not 100% accuracy, but some higher accuracy. So there's zero reproducibility. Okay? Any questions or ideas how to solve it? Well, there's a solution. I mean, don't use it for research. Or whatever you want to share that just, I mean, I think you can basically pay OpenAI for not storing the data, right? Is it possible now? How much is it? Who's paying for ChatGPT? Who's using ChatGPT? You're paying, but you don't know what. Okay, you're paying. No. I mean, seriously, you're giving the data for somebody. Think twice. Okay, so test data leakage. Now let's talk about the evaluation. So we're typically we have some sort of data set, and we're splitting into something where we train our model. So find the best parameters, the data. Then we never touch this. And we train a couple of times, and maybe you have some other part of the data set, which we call validation set, where we just test our trained model and maybe get better or fine-tune the hyperparameters and stuff like that. So there is some cycle here, which is fine. So we do some iterations in finding the best model, blah, blah, blah. And then when we're really ready, then we touch the test data and do the final evaluation. So this will give us some sort of estimation how well the model will generalize to something unseen. Yes, you have a question.
Question about an example about the IBM dataset.
Mm-hmm.
If we have asked ChatGPT to solve it, but never told him if the answer was good or bad, how does it know in the next iteration that he's...
Yeah, it doesn't know the answer, but it will learn something from the test data. And the thing is, that's interesting. If you don't give it the full answers of your problem, well, it will at least, you have an idea.
If you want a different answer, like this is also input that we have it.
Yeah, it's kind of hard. Okay, so I see your point. I see both points. So if you don't tell it the true answer, it will still kind of see the data for pre-training. So the language model will kind of understand the problem better. Okay, this is interesting. So maybe it's not actually solving the problem, because you're not showing the actual solution to the data set. But in one or the other way, it will have seen the test data, like the distribution of words and what is it about? That's interesting. Let me think about it. Okay, yeah, that's a good point. So that's maybe why it doesn't solve like 100% accuracy, because it doesn't remember the solution, but it will have seen the data. Yes.
Also about this thing of model implosion, because it's repeatedly trained on its own generated data.
Mhm.
So
I'm not talking about its own generating data. I'm talking what you type in as a human. So I don't think they're trained on the generated data. It makes no sense, because if you can generate it, why should you train on it? It just trains on something where some human feedback or some human data, like fresh data in a way. Yeah, that's a good point. So that's a good point. I'll think about it. So train validation test. So if you can also do something like cross-validation. So typically it's been a case nowadays, it's kind of out of fashion, but you can do something like split a data set into 5 different faults or chunks, and then iterate. So basically pretend in each run a different part of the data is a training data and different part is a test. So this is you train the model, maybe evaluate, to train the model, evaluate, train the model, evaluate, and so on. They take you the average. It's kind of gives you average generalization error, but it's kind of now out of fashion in NLP. So basically everybody's using train, def, and test split. So if you have a data set, for example, the IMDb, there's a clear train data, clear def data, clear test data. And the reason also is like reproducibility, so everybody's using the same test data. Okay. While in cross-validation, you can kind of do it randomly, and then everybody's doing randomly different things. Okay. Any question? Okay, good. So evaluation of text classification. Now we're getting somewhere. So if we have a binary case, for example, positive and negative classes, so positive review and negative review, then the underlying kind of storage for your results is something called confusion matrix. And it's confusion for a reason, because first it tells you how the predictor confused the true label with something else. And it's confusing also because it's confusing me and other people, because you never know like what's on the y-axis and also the x-axis. Like it's kind of, so you have to know. If you compute something from a confusion matrix, make sure that you understand the columns and the rows, because for example on Wikipedia there's 2 different versions. Like one is this flipped, one the other. It really depends. So make sure you understand what it means. So what it means, if you have 2 classes, so this is saying this was actually negative. So the actual label was 0. And this is saying, this row is saying this label was, the true gold label was positive. So for example, 1. Okay. And then the columns are saying, oh, the predictor said this is 0, and the predictor said this is 1. So this is the semantics of the rows and columns, and you can transpose it, and the semantics will be the same, but you have to understand what is columns and what is rows. So it really varies. Also in different frameworks, it will be shown differently. So never make an assumption, oh, the row is the actual label, because it's not. It could be the predicted label. And now here in this table, we're counting basically if we have an example, so the example number xi and yi is coming in, and we're saying, oh, the actual y was negative and the prediction was negative, then we're adding 1 value here, so the true negatives. So it was actual negative and predicted negative. What if the prediction was wrong? So the actual was 0 and the predicted y hat was 1. So we're getting, okay, actual negative was here and predicted positive here. So we add 1 here. And we're iterating over all test data. And for each of them, we make a prediction and just fill in the confusion matrix. Does it make sense? So then we end up with something. We end up with table where we have numbers, something like that. If our data set is of size 128, then we might end up with something like this confusion matrix. So it's like positive integers in there. So counts basically how many times this happened, okay? So this is how we construct it. Awesome. So this is great. What is it good for? Well, it lets you evaluate the system in very different, many different ways, or various ways. One of them is accuracy. So accuracy can be written as this very ugly formula, which you don't have to remember. But why not? If you want to be pedantic about mathematics, what is it saying basically is how many times was I right? Okay, how many times was I right? So I have this confusion matrix here. Disease detection, I don't know why, but doesn't matter. Disease detection. Okay. So I have this confusion matrix and it's I have these, so actual negative and predicted negative. So these are correct. I was right here and I was right here and I was wrong here and I was wrong here. So how many times out of all the things were I correct? So I'm gonna sum up all these things, the total number of instances, which is 286. And then I'm gonna sum up the diagonal. So these are those which were correct, either correctly predicted negative or correctly predicted as positive, which will give me what? 37 plus 168. And I'm gonna take a fraction of those over all of them, which give me 71% accuracy. Okay. Like basically you're counting, was I right? Was I wrong? Was I right? Was I right? Was I right? And in 71% cases, you are correct. Any questions? Accuracy. So you should know accuracy, like, you know, what accuracy means is basically counting the how many times you were the prediction was correct from all predictions on the test data. Okay, accuracy. Any questions? Good. Shouldn't be surprising. And I don't think the formula is kind of interesting, but why not? I mean, basically the average of all the good predictions. So then there's more important metrics called precision recall and F1 score. And this is where the arbitrariness of columns and rows will become confusing. That's why it's called confusion matrix, because you might remember these things, true positive plus false positive, but these will change if you flip the matrix, you know, so just keep that in mind. So don't remember a formula and just apply it to a confusion matrix unless you really know where these things are. So maybe there is a better way of thinking about those. So precision, and also, you know, precision and recall, and so let's start with precision for class positive, because precision will be different for class negative as well. So let's take precision for this class. And what is it saying? So it's a number true positive. Oh, sorry. No, wrong column. Positive here for this class. So it's the number of true positives divided by true positives plus false positives. Okay. Okay. So what does it mean? It's saying that from all those things that my classifier said they were positive, right? This is this. So these are all instances where my classifier said, oh, this is positive. How many times I was right? Right? Does it make sense? So all the times I said this is positive, how precise were I? Because I can tell everything is positive. I can really say that. I can say like it's gonna be 0, 120, and 0, 110. So this would be my confusion matrix. And accuracy will be 50%. And precision will, what doesn't matter. So precision will be, oh, sorry. My precision, oh, no, sorry. So let's do this. 0, 0, 1. So this is very, very bad predictor. It's saying everything is positive. This is saying everything is positive. But the precision will be what? Will be 1 over 100 plus 1. So the precision will be very, very low because it said everything is positive, but very wrong. Right? So this is a bad predictor. So the precision will be wrong. Any questions to precision? So how many times from all of those, the predictor says positive, how many of them were actually positive? How precise were they? Good. Then let me just delete this. And then we talk about the recall. So again, it's saying for the class positive. So it's saying how many times I was correct over true positive and false negative. So this is this. This is. Let me use different color. So Fn plus Tp. This is this column. So what does it mean? It means so this is all the instances in my training data which are negative, which are actually negative in my training data. So this is saying how many of them I was able to identify from all the training data. So if I had I don't know, if I had 110, then I don't know, 2. So this were my confusion matrix. I have 115 positive instances in my training data, but I was able to identify only 5. So 5 over 115 will give me the precision of, I don't know, something below 7% or 8%, something like that. Sorry, recall. So precision is looking at the, from how many times I said it's positive, it was actually positive. And recall is saying from how many I have in my test data, was I able to find them out. This is how I remember that confusion matrix. There could be other ways. So we have 2 scores now. We have something over, we have precision and we have recall, and then we want to combine them because each of them is saying something a little bit different. And we combine them as a harmonic mean, which is taking the precision and recall and plugging this into the formula. So it's like a average harmonic mean of precision and recall. So it will be a number. So all of those will be between 0 and 1. But typically we don't talk about percent precision. Yeah, maybe we could. Why not? Why not percent precision? So we're saying either 72% precision or 0.72 precision score or F1 score. Okay, any questions to precision, recall, and F1 score? There will be an exercise on that because this is something you should know how to compute that. Okay. Now, I mean, we are just talking about one class, the positive class, and guess what? If we want to do precision and recall for the negative class, will it be the same numbers? Yes or no? No. Okay, so if somebody is reporting a result, for example, for the binary classification or some other classification, and they're saying, oh, the precision and recall and F1 score are this and this and this, then what you have to ask, like, okay, but for which class? You have to be explicit because they are different. You can do it in 2 different ways. So which one is correct? I mean, typically, we're using this for the positive class. So this is like something you want to, for example, classify the disease or kind of find a disease. So if you're running a test for disease, this is what you're interested in. You're not interested in non-disease. So this is kind of a clear assumption. But in some cases, the assumption is like arbitrary. So who knows? So we have to be precise for which class you're computing the precision and recall and report it. Because then you can do this thing for multiple classes, right? I mean, you can compute precision recall for multiple classes. For example, precision for, so this is like document classification. So the precision for wheat would be, I'm taking, so wheat. So this is the diagonal. So this is how many times I was correct on predicting, no, corn. And this is, now let me use different color because we were using that before and they were kind of cute. So this is how many times my classifier said is a corn. So the precision for corn will be 26 over 1 plus 3 plus 26 plus 5, which is some number. Okay, so this will be a precision. And recall will be, oh, how many corn I do have in my data set. So it's going to be 26 over 1 plus 2 plus 13 plus 26 plus 5. And this would be my recall for my class 4. And I can do this for all the classes. And then, so we can compute precision recall, but the F1 score on the complete test set, we can do two things, because if you remember the formula, or you will learn the formula for F1 score, then we have precision recall. I mean, this is the, taking precision recall for the class. Yeah, but we can do some sort of, for each of the classes, we get F1 score. Oops. Okay. No. Sorry, you can't see that. So for each of the classes, we get F1 score. We get F1 score. We get also precision, and we get also recall. So we can average over precision and recall. We can take the average and then compute the overall F1 score, or we can compute each individual F1 scores and then take the average. And you'd be surprised, you will get different results. So again, be very clear. If you report something like computing your evaluation metrics, precision, recall, F1 score for multiple classes, what are you actually reporting? And you can just use this reference. So this is kind of a cute paper about different metrics and how wrong they could be. So details might get tricky. So always report exactly what you do. Always, always, always. Because other people can get different kind of results because they kind of understand your assumptions differently. Okay? Any questions? Good. Evaluation of text generation. Oh, that's getting tricky. So we are talking about text generation tasks last time, and we are talking about, what was that? Machine translation and summarization, question answering, the chit-chat dialogue, right? I mean, continuing the dialogue in a kind of chatty way. And there's very many. There's very many language generation tasks. And the question is like, okay, now we're talking about classification. So we classify text into different categories. It's kind of easy to evaluate. How do you evaluate machine translation, for example? I think we talked about it a little bit last time. Like you have the reference translation, so you need to compare it somehow. But that's getting tricky. Yes?
And can we evaluate the blue score?
We'll get to that exactly. There are metrics. The idea is here to show you a incomplete table which goes even like more like 3 meters, 3 meters below. Like there's so many metrics for evaluating text generation, and there have pros and cons, and there is no single silver bullet. So it's active area of research. How do you evaluate text generation? There's so many ways of doing so. So there are some baseline metrics which everybody should know, and they are, I would say, like suboptimal, but good enough baselines. So one of those, and this is like almost one of the first and most popular metric for machine translation, is the BLEU, bilingual evaluation understudy. BLEU. It sounds French for a reason, I have no idea, but all these metrics actually sound French. So you will see the next one. But let's start with the BLEU. So it's precision-based metrics that computes the n-gram overlap between the reference and the hypothesis. So the hypothesis is something which we generate, and the reference is something in the corpus. And there are multiple references. So what is an n-gram again? What is an n-gram? Oh, we didn't talk about n-grams. Okay, what is an n-gram? So any idea what an n-gram could be?
So as far as I know, it's like a table. It can be multidimensional, and it's basically each column is a word, and for each row, it's probability of the next.
Okay, yeah, you're talking about probabilities of n-grams or language modeling. That's great, but it's too far. So n-gram is basically a tuple of words. So, for example, 2 consecutive words is a bigram. So this is a bigram, this is a bigram, this is a bigram. So basically 2 consecutive words are bigrams. How would be 3 consecutive words? How would you call them? Trigram. trigram, it's 3 consecutive words. How's called just a single word? Monogram, okay, good enough. Any other idea?
Unigram.
Say again?
Unigram.
Unigram, yeah, exactly. This is the terminology. Monogram is cool. I mean, I can't like it, but it's called unigram for a single word. And I think like unigram, bigram, and trigram, and for 4, I think we're just using 4 grams. 4 gram and 5 gram, n-gram. Basically n-gram, and you say, oh, I'm using n-gram and n equals to 3 or something like that. So this is like, but they're special for unigram, bigram, and trigram. So you are measuring the overlap of each n-gram. So each tuple of words, n is a parameter which is decided by the metric. And you're measuring the overlap of these n-grams. And it kind of makes sense. You kind of see, you want to see the overlap, but you're just not looking at single words, but you're looking at phrases, which could be modeled as 3 consecutive words. So if in your reference translation, for example, you see the same phrase as an n-gram as in your generated translation, then it's great. And the more you see the overlaps, the better. But the ordering maybe doesn't matter because you can translate things like with different ordering. So the phrase could be at the beginning of the sentence and then it could be at the end of the sentence, but it still counts as an overlap because why not? You can, shuffle around words. So it's kind of a arbitrary decision of this metric, but it works quite well as a baseline. And it gives you, so it's corpus level metric, so it's important. It gives you score over the entire corpus. So you're not scoring the individual sentences, you're scoring the entire corpus. And the major drawbacks of Blue score, it's precision based. So now we know what's precision and recall. So if it's precision based, it's not recall based, obviously. Doesn't take recall into account. And we have this n-gram exact matching. So yeah, that's an issue because you might actually use a synonym of a word, which would be a good translation, but it will be penalized by the Blue score because it's not like exact kind of translation. So this is one French metric, Blue. Everybody should know that. And there's another one, which again has a French name, which is called Rouge, recall-oriented understudy for gisting evaluation. So I think somebody came up with a kind of cool French sounding name and just found which words should be filled into the abbreviation. I'm pretty sure about it. Because if there's a blue, then you have to be, because blue is, I guess, is it blue? Okay, I don't speak French, but blue is it blue in French? Yeah. And rouge is red. There are so many colors for new metrics. So whatever you do research in metrics, give it a French name, make a metric, and think of the title. Oh, okay. By the way, I should kind of put this away. Sorry, you should have told me how do I put it away? Oops, how do I hide this? Like that. Okay, cool. Good. So let's come back. Blues, okay. Now rouge is the opposite of Blue score because it's similar. It's again n-gram oriented, n-gram matches, but it measures the recall. So I don't want you to understand exactly like computations of these metrics, but you should know like their pros and cons, like what are they oriented to. And we'll have an exercise on actually trying out using software to compute metrics for translation. So you will get your hands dirty if you want. So blue and rouge. So these are things that you should remember. I mean, if you are ever to evaluate something where you generate text, and this is something maybe, I mean, machine translation, absolutely, but something with generation text where you have your gold standard text and what to generate, Blue score and rouge score would be the baseline metrics you want to try. They're better ones. Yes.
So rouge would be mostly for question answering.
Yeah, it kind of tells you what it found. Like, let me see. For question answering, did it generate the content of your sentence? Because it's in your sentence you have n-grams and you wanna generate all of them. So the more you generate the n-grams of your training sentence, of your reference sentence, the better the rouge score will be because it's recall oriented. I don't think it's for question answering. You can do this as well if you want, but it's just one perspective, so to say. But it's a good point, yeah. Yeah. You want so in the precision base in blue score, you want your generated text to be correct. So it has to be it has to be seen before. And in Ruhr score, you wanna generate as much text matching the original as possible. That's my understanding of that. So everything is nice and shiny. Well, it's not, but there's some tricks, tricky parts in benchmarking. For example, so now we are talking about data sets last week and today, evaluating the classification, so precision, recall, F1 score accuracy. And we always assume there is a gold true label, which is true. The ground true is gold data and it's always correct. And it might be if humans agree on this. So for example, if you're labeling data, so does this image contain a bird? Like if you see a bird on the image, everybody, like people would agree on that, right? I mean, there's a bird on the. By the way, do you know these? Oh, this is cute picture of cupcakes and the dogs, the Muppets? No, no Muppets. So there's a couple of there's a grid of images, and some of them are dogs, these cute tiny little dogs, whose names I forgot, and the others are muffins, and they look the same. Do you know this meme? No, come on. It's cute. Let me see. Dog, muffin. So it's kind of hard to label, right? Because you never know. Yeah, but most of the time, if you see an image with a bird, then you say it's a bird, or is learn a verb? I would say, yeah. I mean, we could agree. Or what is the capital of Italy? I mean, so this is kind of easy. But sometimes with language, it's kind of tricky because, for example, if you're labeling comments on Facebook or Instagram or any social media, and you're the poor one who's paid for labeling them for toxicity. Never, don't do this unless you have to, really, because it hurts. And then sometimes you don't know. I mean, is this comment toxic or not? It's subjective. I mean, to whom toxic? To me, maybe I don't care. Maybe some other else people do care. So it's tricky. Language is tricky. And there's human label variation, and it impacts all the steps of the traditional machine learning pipeline. Right? Because we're saying, oh, this is gold standard data. So our model has to be 100% predicting this gold standard label. But there's some variance in the gold standard label in the first place. So it's kind of, is it a problem or is it an opportunity? And there's people saying, well, actually, we should take this into account and take this as an opportunity and build different kind of machine learning paradigms around this kind of variance in the labels and not trying to fit it into like, oh, there's one single true label. So Barbara Planck, a professor at LMU Munich, had this beautiful talk or paper a couple of years back about it. So if you're interested, have a look into that. And humans annotators are also biased because if you're creating a data set, I'm not maybe not like the movie reviews because it's done like over a population. It depends. But it's always biased because who from you writes a movie review? Have you ever written a movie review on the internet? Raise your hand. See, so it's biased in a way because only there is a certain selection of people who write reviews on the internet. Whoever wrote nasty things on the internet? Wait, no, I'm not gonna ask this. No. Like, I mean, if you get the data from the internet or reviews about like products, do you write products on Amazon, like product reviews? The good ones or the bad ones? Sorry, you were saying?
Somebody will write a review if the experience was bad instead of good. So
yeah,
of course there's like it's not an accurate representation.
Yeah, exactly. It's biased. So there is some like bias in the sample. If I don't care, maybe I don't write anything. If I'm really upset or it was really good, or someone is paying me in the restaurant saying, It happened to me two weeks back in the New York, like, oh, I'll give you a discount, but you have to write us a review on Google. We were like, what? So I never write reviews on the internet. And you know, the partner I was sitting with on the lunch, like, no, we're not gonna do this. We're gonna pay the full price. But then I understood why this restaurant has like 4.9 stars on Google Maps. The food was good, by the way. It was really, really good, but you know, there's some skewness or bias in the data. So, and sometimes you pay people to write your data, and if there's the same bias in that. I mean, the selection of people you're paying for writing the data will bring some bias of these human annotators in there. So humans are biased, right? So you have to be concerned if you're creating a data set about diversity of the content. Actually, it's like, is it all these people are maybe writing all the time all the same kind of stuff, or is it like diverse enough for your problem? And then it has been shown by this paper by Geva, Job Goldberg, and Jonathan Berrand that models do not generalize well to examples from annotators that did not contribute to the training set. So again, I mean, there is some distribution shift between the training data and test data because people have different sort of distributions of underlying assumptions about world and language. And also sometimes in your data sets, there are artifacts. And these are sort of like spurious statistics. So you want to build. So a couple of years back, we created a task about whether machines can reason about arguments. And maybe I'm not going into details. It's not important. You can have a look if you want. So we created a data set, and we took all the measures kind of to make high quality data, being unbiased and really high variety, and be like, you know, top-notch data set. And one of these sentences were written by human annotators, and we let them write all these things. And there was one step in this annotation which the workers has to kind of make a negation of the sentence in a way, you know. And we instructed them like, oh, write this in the different words and blah 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 blah. And then we ran this competition and paper, and everything was great and good results. And 2 years later or a year later, Tim Niven came with another paper saying, well, by the way, guys, you screwed up your data sets because it's actually very easy to solve if your model is just it just ignores everything which is in the text. And if the model sees this, which is a negation, if this sees in your data set, it gets accuracy about like 70% or something like that. Yeah, so it's a spurious correlation. It's artifact on the data, which was unknown to us because we didn't know, but we introduced like a bias or artifact in the data, which the models can pick up and solve the problem easily, but by not solving the problem, by just saying like, oh, I see the word, I'm just predicting it's positive or negative or whatever that is, and it's gonna give me like the best scores, and it's true. So once this was fixed in the data by Tim, the accuracy dropped to like random baseline 50%, which this is how it's supposed to be for models which are kind of trying to solve this task, really, because it was a hard task. So there are artifacts in the data sets, just keep this in mind. Which brings me to the end on time. So any questions, any comments, any suggestions? This is not the case. So I'll see you later today. We'll be doing something about evaluation. So something with precision, recall, and accuracy and blue scores. So I'll see you later at 2. Was it 2? Yeah, so sharp at 2. See you later. Thanks.